Hello, my name is Parth Agrawal, and I will be presenting stereoscopic universal perturbations across different architectures and datasets. This is joint work with Zachary Berger, Tian Liu, Stefano Soatto, and Alex Wong at the UCLA Vision Lab. Adversarial perturbations are visually imperceptible signals that are optimized to disrupt the normal operations of a deep neural network. They have been shown to exist for classification. When the perturbation image is added to the input, it introduces large errors in the output of the classifier. For example, here a classification network is fooled to output gibbon instead of panda. They also exist for object detection. In this case, when they are added to the image on the right, the dogs are misdetected as a train or a person. Not only that, they can also affect regression tasks like single image depth prediction, where a perturbation image can be optimized to control the output of the network to produce a specific desired target. For example, on the bottom left, the perturbation can fool the depth prediction network to remove the cyclist from the output. These perturbations are optimized with respect to a specific single image and network trained on a specific dataset. And so it typically does not transfer across networks or datasets. We are interested in perturbations that not only affects a single image, but multiple images or even an entire dataset. These are often referred to as universal adversarial perturbations, even though they are typically universal to each image in a particular dataset and usually do not extend to different datasets. For example, on the bottom right, the same perturbation can cause a camel to be predicted as a sloth and stalking to be predicted as elephant. This is not too surprising for single image-based tasks like classification, detection, or even depth prediction, where there is no unique minimizer for an image. In other words, the image itself does not constrain the output, the training set does. The tasks are purely inductive. Without training data and a strong prior, a single image does not enable the inference of labels of objects. This is not true for stereo, where one is given a pair of images taken by stereo cameras that are typically situated side by side, separated by a fixed distance that we call the baseline, similar to our eyes. Binocular disparity, or the horizontal motion of pixels across a pair of images captured by stereo cameras, is sufficient to uniquely infer depth anywhere in the image where there is sufficiently exciting textures. So there is no need for induction, training, or even a data set to estimate depth. But it turns out that even when the output can be uniquely inferred, like calibrated stereo, the deep neural network can just as easily be fooled. We call this phenomena stereopagnosia. For example, a pair of perturbation images can be optimized to introduce gross errors in the output of deep stereo matching network as shown in these figures. However, the pair of perturbation images only works for a specific neural network for a specific stereo pair from a specific data set. Since individual perturbations had to be crafted for each image, security concerns were far-fetched. But one may wonder if there exists a single perturbation image that transfers across multiple datasets, across multiple domains, that affects multiple network architectures trained in different ways. This is precisely what we aim to answer in this talk. In this work, we show the existence of universal adversarial perturbations for deep stereo networks that we term stereoscopic universal perturbations, or SUPs, where a single set of additive perturbations can be applied effectively to corrupt the disparity estimates of multiple deep stereo networks on different stereo pairs, even without knowledge of the architectures or the way they are trained. Here we have a figure showing images of outdoor driving scenarios from the Kitty dataset, where the same perturbation images are added to different stereo pairs to corrupt the outputs of two different networks, AANet on the top right and PSMNet on the bottom right. Not only that, these SUPs can transfer across datasets and domains. For instance, when added to images from Flying Things 3D, a synthetic dataset comprised of random objects moving across the field of view, the perturbations can disrupt the output of another deep stereo network, deep pruner. Unlike the perturbations we saw earlier that were optimized across the entire image, SUPs are typically a patch that is much smaller in dimensions, for instance, 64 by 64 pixels. This patch is added to a given clean image by evenly repeating or tiling the perturbation without overlap across its height and width to yield a perturbed image. To optimize SUPs, we maximize the difference between the outputs of the network for clean and perturbed stereo pairs and compute the gradient of the loss with respect to the clean images. We average the gradients across all patches and project them onto an L-infinity ball of radius alpha, which serves as a learning rate, and update the perturbations. By introducing this styling scheme, we prevent the perturbations from overfitting to the bias in the image induced by the training set, for instance, having roads on the bottom of the image and sky on the top for outdoor driving. This in turn helps with generalization across images, datasets, and even domains. We repeat these steps iteratively for every sample within a training set and to constrain aggregated perturbations to a specific upper norm so that they remain quasi-imperceptible, we project onto an L-infinity ball of epsilon radius at every step. Here we show some quantitative results for SUPs optimized on the Kitty dataset for AANet. When added to the inputs of Deep Pruner and PSMNet, we increase their D1 error from 1.28% to 52.66% and from 4.25% to 61.66% respectively, as shown on the left plot. Not only that, these same SUPs also disrupts the performance for all of these networks on Flying Things 3D. The right plot shows that the error for AANet increases by nearly 10 times when the perturbations are added to its inputs. To show this qualitatively, here are some point clouds estimated by each network before and after we applied our SUPs to its inputs. The three-dimensional scene becomes distorted, where surfaces are sheared and regions from far away are incorrectly estimated as close. But it turns out that SUPs do not affect all objects populating the scene equally. Some regions, like the sky and vegetation, are much more susceptible. We conjecture that this is due to the inherent ambiguity when establishing correspondences in these homogeneous and textureless regions. So network cannot rely on the observed data, but on the regularizer or prior learned from the training set, where the SUPs have free rein to disrupt the stereo network. This means that the SUPs must be altering the correspondences between left and right image by making regions with similar intensities to be dissimilar in the embedding space. Here we show the correlation between registered features between the left and right images. As expected, the corresponding feature vectors between clean stereo pairs exhibited high correlation as shown on the left. As shown on the right, the perturbed stereo pairs grew more uncorrelated throughout the forward pass, which resulted in incorrect points being matched. But in a surprising twist, we notice that the features produced by AANet becomes more correlated after the 20th layer. It turns out that this curious increase in the correlation coincides with the deformable convolution layers in the network, which motivates the idea of using them as a means to render the deep neural networks more robust to SUPs. To test out our hypothesis, we took PSMNet, the least robust method, and replaced its convolutional layers with deformable convolutions. We observed some fascinating results. The more we replaced, the more robust PSMNet became. We conjecture that this is because deformable convolutions predict convolutional offsets based on the input, which in turn allows them to avoid the adversarial signal. Additionally, we also found that network architectures employing explicit matching modules like patch match or correlation tend to exhibit higher robustness. So by redesigning PSMNet with deformable convolutions and explicit matching, we improved its robustness by 63% as shown by the purple line. which rivals the robustness of networks fine-tuned with the widely used adversarial data augmentation shown in green. Better yet, our design can be used in conjunction with adversarial fine-tuning to achieve even more robust networks, as shown in cyan. Not only does our design mitigate the adversarial effect, they also improve the robustness against common image perturbations that may arise from various corruptions like blurring, short noise, and image compression. On the left, we show a plot of the relative change in error when we introduce these common perturbations into the input images. In red is the error for vanilla PSMNet, and in blue, the same system after incorporating our designs. Overall, we improve an average of 70% in robustness and as much as 80% for corruptions like short noise. This is evident in the point cloud on the right, where we significantly improve the performance when inputs are corrupted by Gaussian blur. So indeed, stereoscopic universal perturbations exist, and not only do they affect the dataset and network they are optimized for, but they can transfer across network architectures, datasets, and even domains. As stereo is widely used in spatial tasks, this may present a concern. But through the analysis of these perturbations and their effect on stereo networks, we have found architectural elements such as deformable convolutions and inductive biases like explicit matching that can be incorporated into the network designs to render them robust. And not only do these designs improve robustness against adversaries, but also to common image perturbations. Nonetheless, this is really the first step. Admittedly, our scope is limited to stereo, but there exist many geometry problems, such as multiview and optical flow, that share similar network architectures. So we hope that our optimistic results can motivate the design of more robust systems. For those interested, our code is available via the QR code and the GitHub link above. Thank you.